Okay, so we're kicking off slightly later than expected, but what we'll aim to do is we've got quite a long lunch break, so we'll claw that time back at lunchtime. So we'll still start the afternoon sessions at 1:30 as is planned in the program. So the lightning talk tracks should be starting at the moment as well to resynchronize with this track. Okay, so to introduce our next speaker, it's a great pleasure to introduce Paul Groth of Elsevier Labs, who's come over from Amsterdam, who will be talking about knowledge graph construction for research and medicine. So big welcome to Paul.
Hey, everybody. Thanks for coming back after coffee, right? We only had 10 minutes, right? So it was like, got to get the coffee in. And actually, your question was really a great intro to this talk. And this is really how we view knowledge graphs as a resource, where we use them in our company, and the challenges that we have and the approaches that we're starting to investigate in order to build out more of an entire knowledge platform within the company. So a little bit background about what Elsevier is. Who are our customers? So our customers are facing challenges, in particular in science and health. Those are our two target areas. If you look at the cost of, or if you look at the global average research spend, it's going up at something like 3.4% a year. So it's a market that's growing. It's a really important market. Research drives innovation and development in our world. A big problem that our researchers face is the lack of tools to be effective. So a large part of our research isn't as reproducible as we might like it. Our pharmaceutical companies face tremendous challenges in bringing new drugs to market. Billions of dollars in order to bring a new drug to market. And you see in doctors' offices, GP clinics, this notion of medical error, right? And that's really a lack of information problem. So our goal is to answer information-based questions for researchers, doctors, and nurses. So these questions look like things like, my work is moving towards a new field, what should I know? What should I read? What's important? Who are the people I should connect to? What's the next organization where I should work? If I'm a university, who should I collaborate with? In the domain of medicine, you know, I'm there. How should I treat my patient given her condition and therapy, right? And how should I master a subject matter? Let's say I'm a nurse and I'm trying to learn to pass my exams. What should I learn next? Where should I read? What is that answer that I need to have? And so if you look across these questions that our customers have, these questions are not about text or documents. They are about things. And I like this quote because it really connects this notion of what traditionally Elsevier is known as, which is a large publisher of content, which we still are, the largest scientific publisher in the world. But it connects that notion of documents to this notion of answers that our customers are looking for. So why shouldn't a search on an author return information about the author? Where the author was born? Where did they live? What she's known for? All of this possible, but only if we make some fundamental changes in our approach to description. The challenge for us lies in transforming what we can have our data into iterated things and not just documents. And so this is where connected data, and in particular the notion of having knowledge graphs, is really important. So I want to tell you what I think knowledge graphs are, because there's a lot of different things. So this is a definition I like, and it's not from me. So if it was from me, you could wonder. But a knowledge graph is a graph-structured knowledge base which stores factual information in form of relationships between entities, these things that we're talking about. And knowledge graphs are really metadata about the world that move beyond the focus of documents to people, concepts, things, and events. And they're really about providing those answers, being that knowledge base for giving people answers. So do we have knowledge graphs in Elsevier today? In fact, some of our bigger products are fundamentally knowledge graphs. So this is the first one. It's called Schemas. And what Schemas is an index of the world's research and the people involved. So if you look at Schemas, what you have is organizations. So this is an example from Elsevier. We have relationships, obviously, to documents, but also to authors, where authors are disambiguated. Precise, we know who the author is. We have relationships from the organizations to works. We also have relationships to particular patents. And we can statistically aggregate around these entities, authors, works, organizations. So those are the kind of the three key entities in Schemas. And now what can you do with that kind of information? This is one of my favorite examples of what you can do with this kind of knowledge graph that is Schemas, is actually give to a city a comparator of how they're performing in research in different domains. So another entity in Schemas that we have using a taxonomy is a breakdown of fields. So we can tell Amsterdam, hey, well, the world average citation rate is something like 1.0. In medicine, you have we have to categorize everything as medicine. You have a lot of output that's pretty good. But by the way, if you look at neuroscience, it's not a lot of output, but you're really great in neuroscience. And then we can compare it to cities like Barcelona. So to do that, we have to understand geography. We have to understand this notion of citation, the links between papers. We have to understand the notions between authors and links to documents. We have to be able to aggregate that at geographical and organizational levels. So that's one product that I would claim is a knowledge graph. Another product that we have is called Reaxys. So Reaxys is one of the world's largest chemistry databases. It has something like, if I remember right, 30 million chemicals, about 500 million relationships. And why is this a knowledge graph? So we have the notion, the entity of a chemical, right? So this is sorafenib. You can link from that chemical to all sorts of things, to its drug likeliness. We can link to reactions. We can link to targets. We can link to preparations. Those are entities in the domain of chemistry that are interesting to chemists, right? Now, we can go back and source that from original documents where we get this information. But what our chemists mostly do with this kind of thing is they go try to find chemicals that are related to targets, and they download a unique chemical representation, usually in the form of a mole file, and then they put it in a simulator. That's what a lot of our chemists do with this. A lot of our drug discovery people use these kind of filters on the side to narrow down their space of chemicals as applied to a given drug target. So this is a knowledge graph as well, I would claim. Now, what I haven't told you is, and it's probably very interesting, to create these knowledge graphs is an expensive proposition. It requires both an automated pipeline, which we have, but a lot of manual curation. And what we've seen is that people want more information in terms of these answers and these kind of knowledge graph designs. And so that's really the problem I'm going to talk about in a little bit more detail. So a little bit of a broad view of where we are going in terms of our information architecture around knowledge graphs. So you can imagine we have with Schemas the beginnings of a knowledge graph around the entirety of research. We have with Reaxys and other products, Pathway Studio, a product called Quosa, beginnings of a graph around the life sciences. We also have graphs around healthcare, and I'll talk about those in a second. And those knowledge graphs are underpinning our upper level applications that we're delivering, also some of our AI algorithms that we're developing. At the bottom are all of the content and data that we're sucking in to integrate, right? So all those, I think we publish 500,000 publications a year. We actually aggregate every publication that's of pretty much any worth. We ingest that. We extract data out of that. So all that information is coming in as well, obviously book content. So we're trying to build this knowledge platform. But this is, to build this in our traditional manner for something like chemistry or a citation database works well, but the problem is we want to go to richer and deeper domains, and we're getting more data all the time. So we're getting kind of this information overload. Just like our customers have all this information coming at us, we have the same problem. So we need more and more automated techniques to do this. Another area is that we get researchers, and in particular, have very small domains that they're interested in, and they would like to understand everything about their own small domain. And what we'd like to do is help them with answers. But how can we do that? So we've been doing some work with the Amsterdam universities as well as Maastricht University, looking at, for example, how researchers search for the data that they need. And this is a survey of essentially all the literature out there on searching for data by researchers. I think two really freaked me out as somebody. Number three. So what a lot of researchers are doing, still to this day, they're reconstructing data tables from journal articles and then building out knowledge graphs themselves, i.e. Excel spreadsheets with everything disambiguated by themselves. That's crazy amounts of work that these high-performing people are having to do. Elsevier should do this for them, right? It's insane, right? We need to do better. So we need to be able to produce these knowledge graphs much faster, and we need to be able to do them at high quality. So I'm going to talk about 3 ways we've been exploring to do that and show you some examples along the way. So the first is machine reading, so natural language processing here. So I'll give you an example for one of our newer knowledge graphs that's really getting deeper into the domain of science. This is what we call Elsevier topic pages. So what we have is searchers who are interested in a new concept, right? So I always pick a thing that I can't pronounce. How do you pronounce that word? Anybody? Armadillo. Right? See, I don't know why I put this on my slide. And they're interested in this. And what people will do is type into Google search that term, and then they'll look at Wikipedia pages. But we have a lot of deep book content that is about that concept that really gives you a way to build up your knowledge in that domain. So what we want to do is build a knowledge graph of all these unique concepts. We want to relate them to other similar concepts. We want to bring out relevant snippets from that book content and present that to the user. And we publish that online and let Google index the hell out of it. So when you now search for that, you'll find that it appears in ScienceDirect, exposing our content out there about this unique concept. So the question is, how do we build that? Well, I won't go to everything in this slide, but what we do is we try to disambiguate concepts. We try to find these definitions automatically, and I'll talk a little bit more about that. Then we need to rank those definitions. We also then need to extract the applicable sections of content from all of our books, right, and rank that as well. And then we need to use that as in an automated way to build that up. So we're using there an ontology that we call Omniscience, which is an ontology or a vocabulary that expresses all of science, pretty much. And we're building that out. So over time, we're using our journal article content to find definitions and book content to find definitions. All right, there we go. So this is the kind of backbone to building those pages, and it's called Omniscience. So Omniscience is an interesting union of a bunch of different taxonomies. So we use public domain taxonomies like WordNet at the very highest level. Then we use journal coding systems that we used for Scopus. We use taxonomies for our journal platform called Science Direct. We have specific editorial taxonomies. And then we have we have fine-grained domain taxonomies. But in the process of building this out, a lot of this kind of upper-level structure is all hand-done by our knowledge representation specialists. So they're sourcing all these concepts and links from everywhere, and then they're putting it together. But what we found in building these topic pages is that kind of taxonomy or ontology wasn't deep enough. So what we did was we invented new algorithms to actually mine definitions of new concepts. So looking for key concepts in our books to add to this ontology. How am I doing on time? Good? Done. Where am I? Let's do this one. So an interesting part of this is part of filling up your knowledge graph is obviously identifying these definitions. So let's say we're trying to find a definition for these kind of concepts here. Well, if you look in our text, that concept is going to appear in lots of different phrases. So if you read this, you'll see that some of these are good definitions just by reading it, and some of these are bad definitions, right? So let's talk about the olfactory bulb. If I read you, the most common sites used for induction of kindling include the amygdala, blah, 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 olfactory bulb, and a cortex. It's not a really great definition of that concept. Whereas over here, we have the olfactory bulb is the first relay station of the central olfactory system. Gives you a pretty precise definition. So we built in this case, it's a simple classification model. I think it's an SVM using about 30 features to automatically classify, is this sentence a good definition or is it not a good definition? And that's how we populate the knowledge graph. So I wanted to just say that this is not just us building these kinds of backbone knowledge graphs, and not just us actually using the combination of our knowledge representation specialists with automation. So I always like this little article from LinkedIn, and they talked about the LinkedIn knowledge graph. Where is it? They say, where is the key thing? Cover. What entities are organic? Oh, where's the phrase? What they say in there, and I'm reading it right now, is essentially they actually combine this automation with a curation step. And I think that's an interesting point in generating these knowledge graphs, is how do we flip, particularly for us, how do we flip from manual first to automation, but automation and then a very important step of curation, similar to what Spiros was talking about this morning, the importance of having that human in the loop. So another couple ideas around how we're doing machine reading. So that's about extracting definitions to populate our knowledge graph. Can we build out our knowledge graph in a more automated way? So one of the things I've been looking at is how do we add new relations into our knowledge graph that we never knew about, right? so we don't have people adding those kinds of relations, but where do we discover them? And so I've gotten really into what we call open information extraction and something called universal schemas. So there's a technique called open information extraction where what you can do is using the structure or the syntactical structure automatically extract subjects, verbs, objects from a sentence and build up triples. And so an example of that is something like this. You can extract things like concept, induced an early increase of another concept, right? And you could just mine that in an unsupervised fashion from text. Now, the problem with that is that you get a lot of triples, right? So in this case, we started out with about 500 million extracted triples. And it's a bit of a mess. So we want to do a couple things. One is we want to bind that to a background knowledge base. So we leave the surface form triples or verbs as they are, relations as they are, and we bind the nouns that we find to actual concepts in our background ontology. So this is about really introducing new relations. And then we use this approach called universal schemas. So this is a cool trick developed by a guy named Andrew McCallum. So what you do is you take all your entities. These are disambiguated entities. You put those entity pairs in your columns or in your rows. In your columns, you express all of your surface form relations, but you also express all the relations that you have in your ontology between those two concepts. Then you factorize the matrix, so very much like a recommender system, right? So you factorize the matrix, and you put it back together. And the interesting thing is that you get a prediction for the likelihood of new relations between those two concepts. And they can be both surface form relations, but also relations already existing in your ontology. So this is a way we can suggest new relations to be added, right? So new relations that are already defined within our knowledge graph, we can suggest those, but we can also suggest completely new relations that our curator should add to the knowledge graph. So this is one approach for trying to mine more of our data to get more relations and build out that knowledge graph that we're looking for, all in a very unsupervised manner up to the end when we want to actually check, yes, go through our curators. So that's one way. Let's read some text, add it to a knowledge graph. Another way we can build knowledge graphs in a different fashion is doing it from data. So this is a graph we've been building. It's called the medical graph. And what we do here is we learn relations from anonymous insurance claims data. So what we want to know in this knowledge graph is to learn, okay, these are particular symptoms or diseases that you have. What is the likelihood that you're going to get another disease, right? So given the likelihood of these diseases, what is the successor disease that you're going to have? So what we do is we learn from our data in a longitudinal way, predictive models that essentially predict whether the association between every individual disease with every other disease. And that correlation, if it's high enough, we express that as an edge in our graph. Now, using that, this is a demo thing. We can actually ask questions like, if you're a 49-year-old man and you're overweight, you have diabetes, you have hypertension, and anxiety disorder, what is the absolute risk of you getting depression within the next 4 years? And so we can look through that graph and just pop up those answers. And the nice thing, the way we built this, is that we can provide The reason why it's nice is it's a graph in the background. So we can actually express the y a bit. Not as good as your y, actually, but somewhat of a y, because that's what people want to know, because we can display to, so these are the blue is the current medications. These are your existing diseases. The red is the likelihood, or the thing you're going to get. And the interesting thing, we can display that to somebody, and they can say, okay, these are high. I agree that these diseases are likely precursors to this other thing, and we can explain why that is. So how are we doing this? So we're building a predictive model for every disease relationship up to the 3-digit ICD code. We essentially take past data, and we try to predict into the future using this claims data. I'm going to skip over the boring stuff of data integration and cleaning, just to say this is what we learn. So based on 3.8 million patients, using their age, gender, all the diagnosis, all their medications, we get about 7,000 features, and we build about 1,600 models for every pair of those factors with the previous factors. And the model we ended up using is just a kind of what's called a generalized linear model. And the reason we use that model and we build all these individual models is to provide the relationships in our knowledge graph. Okay, so that's kind of trying to learn relationships bottom up from data to build out a knowledge graph. Finally, I think this is the last one, is really using knowledge graphs as a backbone to integrate more and more data. So this is another product we have. It's called Clinical Key, and this is a search engine for doctors, right? And it turns out that search for doctors is very different than search for researchers. Researchers spend a lot of time trying to find the requisite material. Doctors don't, right? They quit usually after 3 to 8 minutes of searching. Even if they have a question, they don't know, because they just don't have time. And the backbone of Emmet, or the backbone of Clinical Key, is disambiguated entities that we can search on. And that is this taxonomy that we've built called Emmet. It has about 540,000 concepts once you kind of do some math. And this is all hand curated. So it's about 100 person years of clinical expert knowledge in building out kind of the structure of medicine and the entities that are important in medicine. So that's cool. That's what we have. It's a basis for a knowledge graph that we call an H graph that we're building out. And what's interesting is that it provides us this structure that we can attach additional relationships to. So one of the interesting things we found out is that doctors really like what are called, they like these kind of decision trees, and not in the machine learning sense. Literally, like, okay, we have a male who got up too early this morning in Amsterdam, and he probably needs more coffee, you know, give him coffee, right? These kind of decision trees like this. And we actually have those images of decision trees. We also have tables of, like, if you're a male over 35, you should take this much drug. We also have these kind of tables. So these decision trees, these tables, are really useful. And we have those in our medical textbooks, tons of them. But we need to find them and surface them. So for that, we used kind of the hipness, right? So we used deep learning to, and in particular, a variant of transfer learning, to go through all of our images and classify them into decision trees, to classify them into clinical workflows, to classify them into tables. Great, we've done that classification. And we've classified them per the entities that they're associated with. And that's really the important part now, is that we can attach each of those decision trees or tables directly to an entity within our knowledge graph. And that's cool because now somebody can type something like hypertension, and we can do the lovely kind of box thing that you expect nowadays in search engine, where we surface that selected content that is exactly known to that entity. Now, a final word on using knowledge graphs as a backbone. So like a lot of companies, and I think Elsevier is older than most. It's something like 100, I'm going to get this wrong, like 130 years old. It's an old company. And there's lots of legacy systems. There's lots of existing products that are going around. So you don't want to just upend everything you've already done. And so this is where actually the concepts of linked data are really, really important. So this is what we've been building out for about 7 months, 8 months now, and it's really looking cool. So we have products, one I talked to you about called Clinical Key. We have another product called Order Sets. This is cool. This is documents that actually tell a doctor, okay, here are the things that you need to give to the patient after they leave the hospital for a common diagnosis. A bunch of documents like that. That's hosted, I think, in an Oracle database. Let's see, another one. GSDD is Gold Standard Drug Database. So we take in all the, if you go to the pharmacy, you look at a bottle with that you're getting with pills, it has like all the instructions and all the ingredients on it. We take those all in, we digitize them, or we source them directly from manufacturers. We build a big database of that, and we give that to places like CVS, right, or Walgreens, right? They use in their systems. So we're constantly updating that database. And I believe this one is kind of an Oracle DB written with .NET, right? Our central HGraph core is actually a triple store, currently using GraphDB. Our books database is in Java. So you have this kind of plethora of information. And we're not going to go to every one of those teams because they're delivering value right now and say, hey, get rid of all that stuff, put a graph database in. We don't want to suck everything out of those things because there's whole teams that are keeping all this stuff up to date, right? And we don't want to centralize that process. Those teams have different lines, all this kind of thing. So what we've done is we've put a linked data APIs on top of all those systems as a separate API using a common vocabulary bootstrapped by the one I talked about, Emmett, before. And then what we're able to do is query across those domains. And yeah, it's not super fast if you're doing it in real time, but what that allows us to do is start building those integrations across our different applications, and then also caching that data. So essentially crawling our internal data to build new applications. And so having this backbone vocabulary has been really key to trying to do that data integration problem, right? And using that linked data concept. So to wrap up, I think knowledge graphs are a critical component for delivering customer value. Scopus is a huge product of Elsevier. Reaxis is a huge product of Elsevier. Those are fundamentally about entities related to other entities in the world, making that kind of cohesive database. I think AI techniques such as ML and just predictive modeling from data are key parts to building knowledge graphs faster, right? And I think this notion of using intelligence to build these things is really key as we get more specificity in our requirements. I want detailed data, but also as the pace of change increases. I think it's interesting within Elsevier how we've leveraged existing assets, right? The Emmett ontology the Emmett taxonomy with 100 years of medical knowledge was not built in half a year, right? It was built over the course of tens of years. The Omniscience vocabulary they've developed, we have that's been around for a while. It's based on ontologies that we've already had for a while. Using our existing databases as primers for new knowledge graphs. All of that, kind of don't throw away all that work that's been done. It's really valuable. I have a whole other talk that I'll just start. No. And maybe it's for the panel, about how knowledge graphs are kind of a great foundation for starting to build ML solutions, right? So this was really about using ML to build yourself a knowledge graph to drive applications. But there's this other part of, hey, now that I have this data, can I start developing new recommender systems, new predictive models? And we're hiring. We're also hiring in the connected data space. We actually have a couple very nice offices here in London, right in the center of London. So we're hiring, so come talk to me if you're interested in this kind of stuff. Thanks.
Thanks, Paul. Great talk. Maybe in the interest of time, we'll ask for the panelists to get set up, and whilst they're getting settled, we've got time for a few questions. I'll run this mic up.
How much and how are you using Sparkle, and are you using federated queries across our data sources?
I'll preface that with, to the best of my knowledge, we have about 1,000 technologists that work for Elsevier, so there's always somebody doing things that I don't know. But so we have a number of graph databases. We don't use federated querying. So for our taxonomy management and our ontology management, we host a lot of that in graph databases, in particular GraphDB. We use other graph databases in other domains. Federated querying, what we've seen is that APIs and having APIs where particular applications can call the API they need to retrieve the data is actually a better approach for us. Because, to be honest, most of our developers are very familiar. You give them a JSON endpoint, they can call that if they have the right documentation. They can really build applications fast, and especially end-user applications.
Any questions from this side or the other side? OK, great. Well, big thanks to Paul for a fantastic talk.